Okay. Hello, everyone. My name is Ajay Jacob, and I'm the Director of Projects at California Dreams Hub. Today, I have the pleasure of inviting Professor James Buckwalter from the University of California, Santa Barbara, UCSB. He's a professor of electrical and computer engineering at UCSB, and he's also a fellow of the IEEE. He has received several awards: 2004 IBM PhD Fellowship, 2007 DARPA Young Faculty Award, 2011 NSF Career Award, 2015 IEEE MDTS Young Engineer Award, quite a number of awards. He has published more than 270 conference papers and also journal papers on the research related to RF, millimeter wave, high-speed optoelectronic circuits and systems, and he's a founder and CTO of Pseudolithic. Today, Professor Buckwalter will give a talk on adaptive millimeter wave MIMO front ends for integrated communication and sensing. Jim, the stage is yours.
Thank you for the introduction, Ajay. So today I'm going to be talking a little bit about some work that we've been doing on platforms for sensing that can be attractive from the standpoint of size, weight, and power, such that they could be helpful for bringing much more functional sensing to unmanned autonomous vehicles, such as drones that might be used in search and rescue. We like to think of radars and LiDARs as everyday technologies today, but they're a long way from being very, very powerful sensors that can guide autonomous vehicles and robots through difficult terrain and through difficult environments. And we really like to bring hardware and front-end technologies that will enable unobstructed sensing and communications to these challenging environments. When you look at how sensing in millimeter wave band works, just for those who aren't familiar with how radar and millimeter wave radar work, we typically use some kind of frequency modulated continuous wave to sense the environment around us. That sensing happens by sending out a transmission on that FMCW signal and then looking for the reflection at a receiver and comparing the Doppler shift that's occurred between the transmitted and received signal. Based on the amount of bandwidth that signal uses, we can improve the range resolution of our detection. But we also can use parameters around that chirp behavior in the FMCW signal to improve velocity resolution. But one big problem with traditional millimeter wave radar is that you don't get a lot of lateral detection or angular resolution from a single transmitter and a single receiver. So while there's a lot of benefits to going to higher frequencies in terms of getting that high bandwidth and potentially reducing the wavelength that's used for detecting the velocity of an object, this angular resolution problem still becomes an issue if you're trying to field a system that has to be able to see very small objects at a distance. So a lot of the commercial world in automotive radar has moved towards what's called MIMO, multiple input, multiple output millimeter wave radar. Commercial MIMO chips use multiple TX and RX elements to improve the range resolution by basically bringing multiple elements as transmit and receive at a different point in time so that they can time duplex which transmitter and which receiver are used to do the detection. And this forms what's called a virtual array. The virtual array is the product of the number of transmit objects and the number of receive channels that are used in the MIMO radar. And that product basically shows up as a way that we can improve that angular resolution term. So we get the benefit from MIMO of much better performance in conjunction with the other benefits of going to higher frequencies in radar. So there's an advantage there, but one of the problems we see with these radar signals, these radar front ends, is they're not really well designed for communication. They're not designed to talk to other sensor nodes, and so there's a kind of bottleneck there in the way these sensors might be deployed in an autonomous vehicle. So to bring the integrated communications piece in here, we've looked at UCSB in the past to how to use these MIMO radars in networks and add real-time Wi-Fi as a way to connect multiple MIMO radars together and then do detection of an object in real time across that network of MIMO radars. And so, in today's kind of world, we might have that MIMO sensing front end, which is providing information, analog information about the distance and the velocity of someone who's moving around its field of view. But then the processing would go through an embedded controller, which might do some post-processing of the data, some feature extraction, and then go to a communications layer where ultimately you would send the information to another node where it would have to be processed. And so there's a lot of disadvantages to that model where you have poor latency because the information needs to go through several processing steps and needs to be communicated. And so if you're on a drone or something that needs to respond very quickly, that inherent latency becomes problematic. And so that the kind of future vision of how we might do this sensing is to really bring the comms into the front end, to be able to both do the radar signal processing and the radar front end features in conjunction with the communications front end, where we could ultimately share those features and then use some kind of embedded signal processing, maybe some machine learning to very quickly find out what's interesting, what's a feature, and feed that information back to the operator or to the autonomous vehicle. So these adaptive front ends, one of the things we think about is how much power consumption. This is the power piece of what's difficult in UAVs is how much power is required to do this detection. And as we might have multiple transmitters and multiple receivers that could be equipped for the task of radar at these high frequencies, we have a couple scenarios that we could envision. First of all, the way today's MIMO radars would typically work, we have a uniform number of transmitters and receivers that are all basically operating under static conditions. So they essentially all would see a similar consume a similar amount of power to do the sensing task. What we'd like to do in the future might be to adapt some of these transmitters and receivers in terms of their power consumption to ultimately get a better signal detection from the reflected object. And so we'd like to figure out what's the desirable object from this feature extraction that we might be doing in the sensor, and then how do we consume the least amount of power in the front end based on that feature extraction and make a detection in the least amount of time. So we're looking at how to bring these MIMO systems up to new levels of integration and new levels of performance. One of the ways we're looking at improving millimeter wave radar beyond what the commercially available automotive radars do today is to go to higher frequency bands where there's more bandwidth, and that bandwidth would translate into better range resolution. Of course, there's penalties to going to higher frequencies as well that come from the implementation of the electronics. In particular, if we look at the radar range resolution, the radar SNR equation on the right, there's trade-offs in how much power is available at each transmitter. And generally, that power is going to become more difficult to generate as we move from, for instance, 70 gigahertz up to 140 gigahertz. Additionally, the noise factor that's seen in the receiver will degrade as we go to 140 gigahertz. So we see some penalties there. The one place where we win in the radar range equation for a MIMO system would be in the number of elements. In a particular aperture, in a particular antenna area, we can fit a larger number of transmitter elements into the same area. And so in conjunction with being able to adapt the power of the transmitter and receiver per element, we'd like to know how we could use that larger number of elements to perhaps overcome some lower resolution per element that might be associated with communication or with radar. So now let's look at how we can solve these problems of reconfigurable transmitters and receivers. And first in this talk, I'm going to describe a little bit of research we've been working on in how to build large arrays with nonlinear channels. And this has been a topic we've been working on for a few years now, where we were really after improving the efficiency so that we get as much power at 140 gigahertz as possible. And I'll show some implementations of this that we've done and published at D-band. And then in the later part of the talk, I'm going to describe some of the work we've done in code correlation for radar and how that might influence the way we do adaptive MIMO radar receivers. So today, a linear phased array, much like the type that are commercially available, and a lot of research has been done by colleagues out here at UC San Diego and other places, is usually a linear signal that's upconverted and then sent to multiple channels where it's beamformed in a particular direction. The advantage of this is that the constellation that you're transmitting is typically the constellation that's going in at the IF port over here on the left. So the entire chain is linear, and all you're doing in each of these blocks in the in the transmit chain is amplifying and providing a phase shift to the signal. And so this is great from the standpoint of getting the best possible beam in the right direction, uniform control, and controlling side lobes through tapering of the array. But there's some disadvantages as you go to higher frequencies where the electronics fundamentally don't have as much gain. And one of those problems is, of course, the efficiency of every single block here is penalized at those higher frequencies. And most of the published work out there will generally show efficiency for the entire transmit chain that's under 1%. Additionally, there's a lot of control that goes into this. If you have 5 bits of VGA control and 5 bits of phase shifting control, that's 10 bits per channel. And as you go to hundreds of channels, it means there's a lot of digital control that has to be handled. Instead, we'd like to consider ways that we might remove that linear approach to generating a signal by moving to what we call linear and nonlinear components. This is an old idea. Link is an idea that's been described for about 100 years now. But it basically takes a linear signal and decomposes it into 2 constant envelope signals that can be transmitted by different amplifiers. So on the top here, we can represent the signal as a polar coordinate component with an amplitude and a phase. And then when you create the linear and nonlinear components, you basically create 2 signals, each that have a constant envelope represented by a max and an outphasing phase phi here. And the combination of those 2 signals in a modulator will then reproduce the original linear waveform at the combination point. So we can generate and synthesize that original linear signal from 2 constant envelope signals that are only phase modulated. And this idea has been used in high efficiency amplifiers since the 1930s in the Charret combiner approach. The link is basically used with load modulation networks that produce asymmetric reactance at the output of the 2 power amplifiers. And by having equal and opposite reactances, what this lets you do is get a very high average efficiency even as you back off the power level. And that's an excellent thing to be able to do if you're transmitting comms waveforms where the average efficiency, or sorry, the average power might be 10 dB lower than the peak power. So outphasing gives you a big win over a Class A or a Class B amplifier in terms of efficiency. So my group in the past decade or so has done a couple demonstrations of this type of outphasing approach. A few years back at ISSCC, we did this in silicon germanium at 30 gigahertz and showed that we could get greater than 40% peak efficiency and also about 35% 6 dB back off efficiency. We've also looked at this in silicon on insulator technologies, or a CMOS RF-SOI process. And similarly, we could get very high peak efficiencies and good back off efficiencies relative to more traditional Class B power amplifiers. So the idea originally was, well, if you can do this type of outphasing at millimeter wave bands, that can help us with making more efficient phased arrays, and those more efficient phased arrays will be capable of helping you increase the number of channels they can support. So why not use this outphasing in a phased array? If you can back it off linearly, you can bring in a constant envelope signal from the bottom and use only phase shifts in two channels that are combined at the antenna, both to get the high average efficiency from the signal that you're generating, but also to share the load of the phase shifting in each of these channels. If we're already doing phase shifting for the beam steering, we can also do phase shifting for the signal modulation. So this seemed like a really nifty way to win with the same hardware if you can use the same phase shifters for two different functions. Unfortunately, there's some challenges to doing this, and the challenges include coupling between the antennas. As the antennas steer, as the beam steers in a certain direction, there's a coupling that will be directional, and that coupling introduces a different type of load modulation that's not desirable and doesn't help you achieve this high average efficiency. So this becomes very difficult to do in an array, but the basic idea of trying to preserve this constant envelope modulation in two channels and use a single phase shifter for both beam steering and modulation remained interesting to us, particularly when we went to hundreds of gigahertz where it was difficult to get high efficiency circuits. So the scheme we're describing today is called linear and nonlinear channel arrays, where instead of bringing in a linear signal and amplifying it up through multiple channels and combining it in space, we bring in simply an LO that's distributed to multiple channels, and then we multiply up the frequency to the desired operation frequency, and now bring in just a 2-bit phase shift, and introduce that 2-bit phase shift control to each channel. So after that phase shift, we are generating one of 4 points in the quadrature domain, 0, 90, 180, 270. And then we allow the signal in space to combine such that we can recreate the 16 points shown in the constellation here on the right. So we get the benefit from it, just a 2-bit phase shifter of potentially being able to steer the beam and generate a constellation in free space. The nice thing about this approach is it's first of all constant envelope. The multiplier works at a constant power. The phase shifter works with constant power. The power amplifier works at constant power, and that lets all these circuits be very high efficiency. The other advantage is we can really bring digital modulation directly to the antenna at this phase shifter and allow very fast phase control, even faster than the symbol rate, so such that we can oversample the signal. And that gives us the ability to dither the phase and produce other kinds of filtering that can be used to offset some of the disadvantages of having a low resolution per channel. The nice thing as well is that we've made our control problem a little bit easier. We have fewer control lines per channel, but they're going to operate at a much higher speed. And typically in advanced CMOS processes today, that's a good benefit to have. So how does this low resolution phase shift work? Well, you might be skeptical that 2 bits per channel is sufficient, but even on a 4-channel array, we can show readily that it's not too hard to steer a beam to the left or to the right with plus or minus 30 degrees through the course control at each element. But on top of that, we're able to, we're also able to generate a constellation in each of those directions. So for instance, if I go to the 30-degree direction, I'm able to actually generate 25 discrete points in free space. Those 25 points come from the combinations of the different phases that might be introduced to the 4 channels. And then you can down select to the symbols that you'd like to use in your constellation. For instance, if I want QPSK, I might have four symbols in the constellation. So that seems promising, but perhaps you think that's limiting to only have 25 discrete points. But if you actually go out and start to scale this up to 12 elements, you start to see something that's very, very quickly and asymptotically approaching a fully linear array. So with 12 elements, you can see the type of beam pattern that's possible. There in place of the one that I showed before with just 4 elements. Now we have something that looks like a traditional side lobe pattern in an array. The beam width shrinks, but also we can generate more points in our constellation. So at 0 degrees, 15 degrees, 45 degrees, we get a much richer constellation space that we can sample if we want to generate a certain set of coordinates in the polar domain. So with that kind of proof of concept behind us, let's talk about how we can implement such an array. We looked at building this type of linear and nonlinear channel approach at D-band, 140 gigahertz, where the silicon on insulator technologies are really at the edge of their capability in terms of performance, and where it's very difficult to build efficient circuits. Where power amplifiers, it's hard to get something as high as 20% power added efficiency. And again, overall, the entire transmitter, if you went with a linear approach, might be only a few percent. So here we looked at building something that might have multipliers that went from Ka band, it's around 40 gigahertz, up to 120 gigahertz. And then D-band phase shifters that select one of 4 phases, and then a multi-stage power amplifier that's then combined to one of 4 channels. Again, 2-bit phase shifters are being used here, but these phase shifters are very high speed. They're capable of being modulated at with more than 10 gigahertz of bandwidth. So we're trying to provide that extra degree of freedom here compared to the kind of commercially available MIMO transmitters that you might find in automotive radar by giving yourself that high speed phase shift to do the modulation. And this work was presented this year by my student Justin Kim at RFIC. The technology we're using for this, just to give you a bit of a background on the 22 nanometer fully depleted SOI that we used here, is really, it's quite a good choice for this type of integration where you have very high speed digital and very high frequency RF circuits. And so this 22FDX process gives us great transistors, the best we can really hope for. They have when you extract the F max of the transistor up to the C3 metal layer, it's around 330 gigahertz F max in our particular instantiation. And you can probably optimize this a little bit more, but these are more than adequate to build circuits up to 140 gigahertz. And so to kind of pinpoint how this is used, I'm not going to go through a lot of circuit details today and keep this kind of high level, but we've published papers that have described how we can build the multipliers and the power amplifiers that would be used in this process in multiple conference papers. The multiplier in this technology can operate with a drain efficiency that's around 10%. So that's the output power of the multiplier relative to the DC power that's consumed. So that's pretty efficient. We can use passive phase shifters that are essentially selecting one of 4 phases. Those have relatively low loss, shown here around 2 to 3 dB of loss across 115 to 130 gigahertz. And then again, the power amplifiers to get to 15 dBm with fairly conservative amounts of gain, 27 dB of gain. We have power amplifiers that are around 12% efficient. So everything here is really being optimized to be as efficient as possible in our channel. Just to show you how this digital phase modulation works at high speeds, we use a hot code. So essentially 4 paths that can be selected at 140 gigahertz. So the signal passes through one of 4 RF channels. And by using that hot coded approach, we have basically simple RF switches that are being activated for 100 picoseconds at a time. So the on-off time constant can be very, very quick. And these are some of our circuit simulations with a random set of codes on the 4 different channels going to the phase shifter, and you can see at 10 gigabits per second here, this is more than adequate time constant. Additionally, the phase shifter can be really trimmed to be as low RMS phase and gain error across the bandwidth. In this case, we're dealing with about 7 degrees of maximum phase error across the entire frequency band that we were targeting, and about under a dB, basically between 110 and 140. Some preliminary work on this was shown in a silicon germanium HBT technology previously, a couple of years back. We're also thinking in these solutions about how to integrate the chip on a interposer. And in this case, we were very concerned with how to get our signals, which we're generating very precious amounts of output power, and we're trying to optimize the efficiency of everything. It means that we can't incur lots of losses on an interposer to get into antennas. And so we spent a lot of time thinking about packaging technologies as well, and how to flip chip an RFIC onto that interposer. In this project, we used LTCC, and shown here where we had a SIW waveguides that were used to get very little loss from the chip to the antennas, and then we had Vivaldi antennas, which were used as the radiators for the 4-channel array. We see LTC as being very promising for RF approaches because it really has the right trade space between the pitch density we're dealing with, the amount of power we can handle with it, heat dissipation, and also RF performance. So taking that LTCC, this is what a module that we built looks like. The 4-channel array on the right, on the left. One of the key features about this that should be pointed out is we were easily able to fit 4 channels in a 4 by 4 millimeter square area. And in fact, on our later generations that we haven't published yet, we're able to compact this even more. So we're able to get a chip that basically can satisfy 1 millimeter pitch spacing at 140 gigahertz in a 2-dimensional array. So even though we're showing a linear array today, we think there's room for us to shrink these chips and build pretty compact transmitters. The chip is flip chipped onto the LTCC. That's then mounted onto a metal carrier alongside a PCB and wire bonded to the PCB, as shown over here on the right. The LTCC is true color here. It's blue, and you can see the Vivaldi radiators to the north of the PCB. Overall, this chip dissipates about 300 milliwatts per element to get 30 milliwatts of output power out. So some measurements we've done. We again published this at RFIC last year. That we've mounted this in our lab and taken some antenna measurements, and we're continuing to improve our measurement capabilities at 140 gigahertz. So this was sampling of the beams that we could form in 3 different directions, bore sight, and then plus or minus 25 degrees. Some of the modulation we were able to generate, this is an 8 PSK signal at 1.5 gigabits per second, and then the power that we were able to send in that 8 PSK direction at minus 25 degrees. We've also been looking at now how to use this with FMCW radar. So to get back to the radar story, compared to the conventional automotive radar that might have gigahertz or so of bandwidth, we can push our radar up to about 12 gigahertz of bandwidth. And the benefit of that from the radar resolution equation I showed on in the introduction is that we should get essentially nearly a factor of 10 better range resolution in theory. So we've been experimenting with this in our lab, comparing our range resolution through detecting nearby objects that are placed in the anechoic chamber at different locations. And so far, we've been able to show with our post-processing that we can detect 2 spheres that are about 3 centimeters apart. So now let me move on to how we might use this transmitter, use the combination of high bandwidth modulation, the comms functions, in support of radar. And this comes back to some work that we did through a DARPA program about 8 years ago called SPAR, Signal Processing at RF. We did this work down at about 2 gigahertz, 1 to 2 gigahertz, where we were trying to think about ways that we could have co-located transmitters and receivers that might be capable of rejecting self-interference. So the transmitter might be 30 dBm, 40 dBm of power. That would jam a receiver that's right next to it. And so how might we do signal processing that's located directly at the antenna to eliminate that very strong transmit signal? And the approach that I worked on in this was to generate what we called code selective filters. These code selective filters were high linearity CMOS circuits that were basically able to let some signals that had the desired code pass while rejecting signals that had the non-desired code, the undesired code. Any other code that's that you could create would be rejected by the code selective filter. And so in conjunction with some high power direct sequence modulators that we could use to imprint the code on an RF carrier, we had the code selective filter to reject the signal on the receive path, and then develop some algorithms to rapidly synchronize the codes at the transmitter and the receiver. So these codes, if you want to think about what this code looks like, it really comes back to something that's like a comm signal. It can be a digital sequence of ones and minus ones, or if you go into the QPSK, you can do combinations of phases. But you can create a code book based on the length of the code. This is a so-called Walsh code or Hadamard code. If you have code of length 8, then you'll have 8 different unique codes, and only when the same code is introduced to a template does it autocorrelate to a delta function, and you let the signal go through. So we use this type of approach where this Walsh code could be used in the receiver by very quickly modulating the receiver's behavior, such that we would reject a cosite signal while letting a desired signal go through. And then, of course, if you want to have multiple access, then you would assign people different codes so that they could simultaneously use the same network. So the solution that we developed at 1 gigahertz and is inspiring some of our work today, basically use this code selective notch filter to first, on the receive path, knock out that strong transmit cosite interference, and then look for the desired signal in a code bandpass filter. And then only after we've gone through that notch and that bandpass would we hit the LNA where we'd recover our signal and then down convert it to GM cells. So this kind of combination of multiple end-path filters that are tuned to look for certain codes gave us the ability to get about 52 dB of rejection. If you see the code pass on the bottom here, the code pass in the black shows the code going through, and the code that's being rejected is in red, and that shows that you're pushing the code power down, but then also pushing it out in frequency to a higher 50 megahertz baseband, where it can be filtered more easily. So, showing how this worked in a real system, we actually connected this up with antennas, used this at about 1 gigahertz with about 100 megahertz of modulation bandwidth. So it's a fairly wide band type of modulation at 1 gigahertz. And we're doing that so that we can very quickly modulate the signal with these codes. The neat thing about this, it didn't consume lots of power. It was about 90 milliwatts of power consumption. In the RF, from the RF front end, it was only about a 4.5 dB noise figure penalty compared to just having an LNA. But then in terms of interference, the really neat thing is we could tolerate 20 dB larger signals than from the interferer than our actual signal, and still get relatively good clean eye diagrams out of this circuit. So we could bring a lot of power in and still recover the desired signal, even though it's being swamped by that transmit signal. But this gave us some interesting insights. If we can do this kind of code correlation at an antenna, why can't we look at capturing multipath signals with different lags and combining all these multipath signals that might be transmitted from one point in space to another point in space, and improve the SNR of our receiver. So rather than thinking about this as a problem of rejecting the co-site interferer, we can improve signal to noise ratio by correlating at different points in time the multipath components of the received signal and adding them all up together, such that you can ultimately pull the signal here shown in red out of the noise. And so we actually were able to do that. We built a receiver that had a rake receiver, essentially, that had multiple fingers that were all operating simultaneously around the LNA. And each of these fingers would down convert a different time delayed version of the received signal. So shown here, we have different correlation paths with different time lags. And each of these time lags corresponds to a different multipath component. And in each of those multipath components, we're able to recover the QPSK signal and get about a 9 dB improvement in our SNR. So this is something we published back in 2020, but it gave some inspiration for what we might do at 140 gigahertz. If we, instead of doing this time division duplexing, where the amount of power that's transmitted from the aperture is limited to one antenna each period, we can transmit simultaneously across our entire array from each of the power amplifiers by putting unique codes onto the signals of each of those antennas. So rather than just transmitting the FMCW that we presented earlier as a radar waveform, rather than just sending FMCW to each of these antennas, we tag each of the antennas with a different Walsh code. So we have this phase shift that can be superimposed upon the FMCW frequency shift, and then rely on the receiver to figure out which code it wants to decorrelate and which transmitter it's going to listen to at a time. And so this gives us a lot of ability to reconfigure how the radar works by using all of the elements at once and allowing the receivers to figure out which of the transmitted signals are most relevant. So now we have a way to adapt a MIMO radar that's unique compared to how things are done today. We can imagine reconfiguration for broad search, being able to look over a wide field of view, and do the typical MIMO processing, or use beam steering to focus our attention in a certain direction, even do beam nulling to disregard features. And this Walsh coding also provides some level of security and resilience to jamming signals if we're able to correlate with those Walsh codes in the receive path. So there's ways we can use the radar waveform to different tasks in both radar and in communications. So finally, how does this fit in with receivers? And we've been thinking a lot about that adaptive receiver piece. How do we control the amount of power that's needed for a certain task, a certain reflected signal that we see in the field of view from a radar waveform. So we've been looking at how to use receivers that can dial their noise appropriate to the task that's being undertaken, and done these comparisons by looking at both phased array approaches and MIMO arrays. If you look at how a receiver array will work, basically if you're very close to the reflection, then you expect that there's going to be a strong reflected signal from a nearby object. And what that means is that your receiver doesn't need to operate at its best possible sensitivity. Instead, it could relax its sensitivity if it can save power and work with a higher noise figure. So what we've been looking at is if we have different configurations of transmitters and receivers. So 4x4 means 4 transmitters, 4 receivers, or 1 transmitter, 8 receivers. We can see different solutions in terms of how much power is required in the receiver and how much noise figure is required. And as I described, as you get farther and farther away from the receiver, then the noise figure has to go down and the power consumption of the array has to go up. Of course, one thing we see here is it's always good to be working in a phased array. Generally, that's saving us power. If we can focus in a particular direction, put our attention in one direction, generally we're focusing energy in the right place, and the power consumption of the phased array is going to be lower than if we're operating in that wide field of view MIMO type of space and looking everywhere. So that's a clear trade-off that we can win if we know where to look, and that comes back to doing this feature extraction and adapting the front end to focus in certain directions. So in some of the work we've been doing is trying to figure out how to implement that kind of delicate noise figure trade-off with power savings. How do you save power in a traditional IQ receiver? Well, it turns out at 100 gigahertz, a lot of power goes into the LO distribution. Most of our power actually goes into multiplying the LO up to the mixer, and then mixing the signals down through some lossy mixers. Usually we use passive, but in this case we used active mixers. And here you can see the trade space that we were exploring on the lower right. There's a circuit schematic. I don't want to dig into too many of the details, but the idea was, if I want to adapt the noise figure of my receiver, all I need to do is change the amount of LO input power I give it. And as I change that LO input power, I should dynamically see a change in the conversion gain. And we built some control feedback here, some adaptation that allowed us to keep the mixer operating with higher conversion gain, even as we back that LO power down. So as opposed to having a static bias where as the LO power went down to, let's say, minus 10 dBm, the conversion gain was now minus 25. Instead, with our feedback circuit, we could back that power down, but keep the conversion gain 17 dB higher at around minus 8 dBm. So that was an interesting insight, that if we had the right adaptation loops on chip, we could dynamically change the LO input power and get this trade-off in our conversion gain. So we've been building that concept up here now, where we have more sophisticated solutions that can integrate LNAs with antennas and build the full receive chain in an array, and explore that LO power trade space for dynamic channels. And so the work we're doing now, showing a receiver here, a 4-element receiver. We actually worked with Georgia Tech to build a glass interposer and wire bonded the chip to that glass interposer. That's all been placed here on this board. It's hard to see on the board, of course, because the PCB dwarfs the chip in the glass. And then we have 8 different connectors here for I and Q signals coming out of the array. This chip is a little more sophisticated because now we're also trying to build this adaptation in. Not all the adaptation is on chip right now. We currently use microcontrollers to help us monitor the signals, provide feedback to some kind of embedded microcontroller, and then come back to this power management module that will then adapt the biasing on the receiver to try to find the right amount of power for the task it's doing. So, down the road, just as a kind of takeaway vision, these sensors, if I have hundreds of these type of MIMO transmitters or receivers, this leads us to a place where we might ultimately find an analog data deluge, lots of information coming from these arrays. And so even with this 4-element array, 8 different SMA connectors here, all high, all possibly very high speed signals. So we might need to have very fast ADCs on the back end. And that leads to this problem of how do we handle all the data that a sensor might generate, and how do we constrain the power dissipation if we're going to put it on something as sensitive to swap as an autonomous vehicle. So instead of letting that power dissipation become unmanageable through lots of analog to digital conversion, lots of passing things back to host processors, and then letting that host processor take action, we're looking at different ways of bringing that adaptation to the RF front end. And so we're thinking more about in our cognitive work now, funded through Cognizant's SRC Center, how we can provide feedback control that's embedded at the front end circuit to do this analog to feature extraction and feedback control of the front end circuitry without going all the way back to the host and doing this decision planning and action as part of that feedback loop. Again, the long latency that we want to prevent that I talked about at the beginning. So a lot of this we believe has biological inspiration, of course. We're obviously integrating lots of information and then processing it with a much lower sampling rate in our brains than we're receiving information through our eyes. And so we're trying to borrow these kinds of ideas and think about how these the necessary adaptation loops can be built into the millimeter wave radar. So ultimately, what we see in Cognizance in our center is how we might merge not only radar but bring LiDAR into the same aperture so that we can jointly use multiple types of modalities for sensing. You could go beyond LiDAR and think about acoustics too. All these different sensors could be part of the information space that's provided to this analog to feature extraction, analog to insight engine shown here, that's providing feedback control to the front end and telling that front end sensor how to use power in a very instantaneous, localized way. And we see the ability to put a lot of this into microchips, into microscale solutions. The RFSOI I showed you today is one of those parts, but also the analog to insight might be on some very fine line CMOS processes that would be efficient for the digital implementations. We could have power management circuits all sitting on interposers or print circuit boards in relatively small form factor. And so we see that as a very interesting pathway to building the next generation of autonomous vehicles like UAVs that are able to both sense the world around them as well as communicate. So in conclusion, this is work we've been doing through the SRC. These are some of the sponsors here at the bottom. We see a lot of opportunity to bring D-band to some exciting applications for integrated sensing and communication, particularly where there's this swap space that requires small apertures, and we see an excellent resolution for sensing. And we see opportunities for new transmit and receive architectures in large arrays, ways that we can rethink the way a phased array is built so that it's operating with better efficiency. And the approach I provided today was this linear and nonlinear channel where we have low resolution, rapid phase modulation on each of these transmit channels, and that supports not only radar, but also communications. And then, of course, the receiver adaptation that I showed, how we can take the receive channel and think of it not as a static circuit, but as something that's able to adapt to the signal task at hand, dynamically change the amount of power that is used in each of those receive channels at the penalty of noise figure when it's something that we can compromise. And then finally, how we might use code correlation and decorrelation in the receiver to track different coded MIMO components. So I'm pretty excited to see how we can bring a much faster signal processing to the front end and do very complicated correlation functions. So with that, happy to take questions.
Thank you, Jim. It's a great presentation, lots of information. We have two questions that came online. So one is from John Lauseth. John, do you want to ask the question?
Hi, John.
Hi, John.
Should I view the question or?
Okay, let me read the question. Oh, raise the hand. So yeah. Amy, let me see how I can.
Hi, Jim. I about have audio now.
Okay.
Okay,
Hi.
Great.
Yeah, it was John Lauseth from Collins Aerospace. I was wondering, Jim, about if you only have 2 bits that you're working with to try to save that power and use the link approach, do you have trouble with calibration? Either you're going to be low on ERP or having trouble making the constellation EVM good if you can't calibrate phase shifter differences because you only have 2 bits?
Yeah, that's an excellent question. We're working through that now, actually, in our testing. One of the things I showed you too is, we don't have zero RMS or phase error, but the thing we do have is the ability to oversample the signal, right? So if we can dither the phases very quickly, we can probably calibrate out some of the imperfections in only having 2 bits, right? And if you have enough elements in the array, you have the ability to do some kind of averaging across that larger aperture, larger number of elements. We're thinking 16 elements in our test bed, but we might be able to envision, with enough funding, being able to do hundreds of elements all at once, right? So there's certainly going to be calibration problems. Timing skews become sensitive, and when we're using digital clocks to kind of bring everything in and sync them at each chip with a master clock, right? But the idea certainly is that you can calibrate out some of this. It's not going to be as good as the kind of adjacent channel emissions that you might deal with in cell networks, right? With the kind of emissions that are tolerable. Because we're at 100 gigahertz, we're not that worried about it, right? There's not really a lot of concern with emissions at the frequency bands we're considering right now. But down the road, of course, you may start to get more interested in how much power is being leaked into adjacent channels.
Yeah, thanks.
Great. Jim, the next question is from an anonymous attendee, and the question is, are there any advantage in going to terahertz frequencies for automotive radar applications? And if there is no advantage, what are the main challenge?
Yeah, I think a lot of the automotive folks would think it was crazy to go to 140 gigahertz. So I think we're already just going up by a factor of 2 in frequency. We're already going out of the envelope of what the commercial folks are thinking is reasonable. It comes back to this radar range equation I showed at the beginning. The penalties really come around how much power you can get out of the process. In silicon, it's going to be really hard to get any substantial amount of power out above, I'd say, 200-300 gigahertz. We're trying to walk the line between efficiency and power generation right now. And I think 140 is kind of where things start to fall off. But you could probably get power. I mean, there's work out of folks at MIT. They've built radars at 300 gigahertz in silicon. So there's work out there where people have certainly made transmitters that work at 300 gigahertz. Beyond that, silicon really starts to peter out completely. You don't have an F max that's high enough to generate any appreciable gain, and so you're not going to get a lot of power out. You might be able to leak a little bit of power, but it's not going to go very far. Even at D band, the type of path loss that you're going to see is going to keep you at around a couple hundred meters. So you're kind of up against physics at some level. As you go to terahertz, you're going to be dealing with a very large amount of loss here because of the lambda squared part of the SNR equation. So yeah, both power that's available and the noise figure that's possible in silicon are going to be another practical limitation. If you went beyond silicon to maybe some 3.5 technologies, you might be able to get a little better performance, but you're still going to be up against kind of the fundamental physics for radar at a terahertz band. You're probably moving to LiDAR at that point.
Great. Thank you, Jim. Any other questions? It seems there are no questions. I have one question, Jim. So, in your packaging approach, where you're doing this antenna package, do you implement some type of an STCO methodology? Because we are dealing with 140 gigahertz, and this is probably in the 60A regime. And there is a lot of thermal issues that is probably going to impact, and lots of other issues as well.
Yeah, sorry. Yeah, so you're asking specifically about the thermals. Yeah, it's a problem. This chip gets hot. I mean, this
Yeah.
if we leave this in the anechoic chamber with the door closed, you know, I'm not going to say you could cook a turkey, but it gets warm. This, you know, of course, I'm highlighting that we have very high efficiency. We need the high efficiency if we want to transmit any amount of power because of those thermal limitations at the end of the day. As I'm indicating here, you know, if we have 4 elements, 4 channels that are consuming 300 milliwatts each, you know, this is dissipating about 1.2 watts, right? Which maybe is okay for a short lifetime mission. We could put, you know, and we have tried to put heat sinks on this. It becomes a bit of a problem to keep them away from the antennas, right? Because the heat sink will start to become part of the electromagnetic environment around here. You know, in this current chip, most of the heat's going through the LTCC and into, you know, we're hoping through the LTCC and into the metal carrier, but the LTCC is relatively thick. I think it's about 800 microns here. So you can get a little bit of heat through the flip chip balls and into the LTCC, but really you want to have a heat sink on the backside of this RFIC. But at 1.2 watts, I think it's manageable, right? We're not stressing the process too much. If you go to more, if you need to put more channels or increase the power per channel, it's going to become a problem for this type of integration.
Okay. And the antenna, you think the antenna, because this is in the package itself, I mean, it's going to be intact.
Yeah, the antennas, they're essentially sticking off the top here away from the metal carrier. So you can't see the backside of this, but there's actually a notch in the carrier, so in the metal carrier, so that the antennas are not interacting with it, and a ground plane underneath the LTCC. So there's not I think a major issue here with our antennas and the thermals from the chip.
Great. Thank you, Jim. Let's give a round of applause for this great presentation. Jim, thank you so very much.
Thank you for the invitation.
Amy, you can. Amy's slides are still coming up.
I can stop sharing.
Oh yeah, that's okay. I think Amy has now shared. So next week, we have a presentation from Osdal Boras from UC Irvine. That's November 21. And let's meet next week. Thank you all very much for attending this.
Thank you.